A whir is a device or overflow structure that is placed normal to the direction of flow. The whir essentially backs up water so that in flowing over the whir, the water goes through critical depth. Whirs have been used for the measurement of water flow in open channels for many years. Whirs can generally be classified as sharp-crested whirs and broad-crested whirs. Whirs are discussed in detail in 13, 14, and 15. A sharp-crested whir is basically a thin plate mounted perpendicular to the flow, with the top of the plate having a beveled, sharp edge, which makes the nap spring clear from the plate. See figure 11.10. The rate of flow is determined by measuring the head, typically in a stilling well, at a distance upstream from the crest. The head, H, is measured using a gauge. These sharp-crested whirs are as wide as the channel, and the width of the nap is the same length as the crest. Referring to figure 11.10, consider an elemental area and assume the velocity, then the elemental flow is shown. The discharge is expressed by integrating equation 11.44 over the area above the top of the whir crest. Friction effects have been neglected in the deviation of equation 11.45. The drawdown effect, shown in figure 11, and the crest contraction indicate that the streamlines are not parallel or normal to the area in the plane. To account for these effects, a coefficient of discharge, C sub A, is used so that where C is approximately 0.62, this is the basic equation for a suppressed rectangular whir, which can be expressed more generally, as where the C is the whir coefficient and the C sub 3. For U.S. customary units, it is a unit of C equals 1.45. Bronze or broad-crested whirs are essentially critical depth whirs, in that if the whirs are high enough, critical depth occurs on the crest of the whir. For critical flow conditions, use the rectangular channels, or, assuming the approach velocity is negligible, illustrate it by a broad-crested whir installation in a concrete-lined canal. A rectangular, sharp-crested, suppressed whir 3 in 3 millimeters long is 1 millimeter high. Determine the discharge when the head is 150 millimeters. Given geometry and head of a rectangular, sharp-crested, suppressed whir. Find discharge flow rate Q. Solution: use the appropriate whir discharge equation. In this chapter, we investigated steady, uniform flow in a channel and used energy and momentum concepts to derive Cheesy's and Manning's equations. Applied the energy and momentum equations for a controlled volume to non-uniform flow in an open channel. Developed the notion of specific energy of a flow and derived the Froude number for determining whether or not a flow is subcritical, critical, or supercritical. Derived an expression for the specific force for a flow. Investigated some basic concepts of gradually varied flows. Investigated rapidly varied flows, especially the hydraulic jump. We also learned how to use many of the important concepts mentioned above in analyzing a range of real-world open channel flow problems. Note, most of the useful equations in the table below have a number of constraints. Be sure to refer to their page numbers for details. There are, for instance, the Cheesy equation, the Manning equation, the criterion for turbulent flow, the total head or energy head, specific energy in terms of velocity, criteria for critical flow, and a criterion for critical flow of the rectangular channel. Determine the uniform flow depth in a rectangular channel 2.5 millimeters wide with a discharge of 3 millimeters or milliliters. The slope is 0.04 and Manning's roughness factor is 0.01. Determine the uniform flow depth in a trapezoidal channel with a bottom width of 8 feet and side slope of 1 vertical to 2 horizontal. How's that? Too fast? How'd it come out? You want to turn this off?
So.